Hello everyone, welcome to our channel. Today we'll talk about comparison of functor, applicative, and monad. And as we know that monoid, functor, applicative, and monads is kind of basic and common and very important type class when we programming with Haskell. In this video, we will discuss about the relationship between each type class, monoid, functor, applicative, and monad. And you can discover more with the link to the relevant video as below. Almost here is recorded in Vietnamese. So the English version of this will be coming soon. So let's start. So first, we will review about the type signature of this main function of each type class. I will start with the function application. This is the type signature of what we call function application. So we have the type signature of function application is a function take A to B in parentheses, and then to A and then to B. So this is type signature of the function application, and we always see some function written like this, which is the same as print and then show A in parentheses. So let's write a code related to this. So if we have this function print something and we use the show A, A is not in scope or because we have no variable A, so let's set A equal to something in string, and then we call print so A. So it's kind of like print out something. So we can write in the original form or in another form of this is so A. So we have the question is why this line of code and this line of code have the same result, because this one function application and had the type of this is a function take an A to B in parentheses and to A and to B. So let's break down and explain why type of is like this and why it have the same result when we using this one and this one. So let's say that function f has signature. I mean, in every function in Haskell, if we saying that like a function, it means that it will have a type signature like function take an A and return an B. So we have this kind of like equivalent transformation as below. So let's say that we have the type of f is a function take an A and return B. And if we apply f to A, it means that like we move A from the right hand side to the left hand side here. So f and A, apply f to A, we will have the type of it is B. And then because the type of f is a function from A to B, so we replace f in the right hand side of this is equal to A to B in parentheses, and then arrow A. So the type of this one in the left hand side is now still B, right? And then we moving or we change B from the right hand side to the left, or we can write as here. So A to B in parentheses and to A and to B, which is equal or like either type signature of function application. So it means that that's the reason why we have the type of function application is like this. And in many cases, we use that many times, but we don't know why is it have the same result when we using dollar here or we using print and show A in parentheses. So that's the reason why function application had the type like this. Okay, that is the function application, and I spend time to explain about it because it's very important and we use it a lot. But at the beginning of time when I try to learn Haskell, I still wonder a lot about that, and I don't have kind of like reasonable answer for this. So I think this is one way to explain about that and know the reason why the type is like that, and it make us easier to understand and learning Haskell. The next one is Monoid, and the main function of this is a mappend function, or this is the most important function of Monoid, and we can see that this is the angle bracket is the same type of mappend, another way to write it. So mappend is a function which is receive two parameter m to m and return m, and m must be a semigroup. And as you already know that Monoid is has a associated binary operation and identity value. Let's check again. For example, this is the data Monoid, and I will check the info of the sum. So they have, this is the Monoid, right? Now I will check the info of Monoid. So info of Monoid, so we must have kind of like associated binary operation. Binaries mean like we have two params. Associative mean like we can use parentheses here or parentheses here. And then we must have the memtu value, which is identity value. So for example, in the product, we will have the memtu value is 1. In the some data type, we have the memty or identity number is 0. So let's see, let's check. We have some 1, and if we, oh no, some 10, for example, and then empty, and then 10, because 10 plus 0 is 10. Let's say we have product 10, no, 20, and then we empty with the identity value of it is, which is now is 1. So we have the product is 20. Now we can get the product. So normally we can use like this, but it's kind of like lazy to write something like this, but which is equivalent. So that's the reason why I spend time to explain this operator $1. So it's kind of like function application. So it's about the monoid. I mean, the most important thing or the best way to visualize monoid or understand monoid is kind of like we have a function which is kind of like associated binary operation, and the result is which is have the same types of the type of two parameter. So you can see that like the type of A, the type of B, and the type of C, which is have the same type. So monoid as the original, the structure of monoid or like in the mappend function is do not change after we apply the mappend function. Okay, next one. So this is just kind of like the example of the mappend function, which is receive the string and the string and the string, and the final result type of it is string as well. Let's check. So let's check the type of this one. So it's key. It is list of car. So list of car is kind of string, right? So this type of it is string. This is string and a string. So you can see that like monoid, after like we apply the mappend function, the type of the mappend function, the result of the mappend function is keep the same structure as the parameter, right? Next one is the functor. So as you know that like the Fmap function, which is had this type, so we have a function from A to B in parentheses, and the next parameter is FA, and then return FB. So the number A, the value A here is a value inside a structure F. So, and the function here, function from A to B, which is outside of the F structure. So we have this kind of image, which is visualization of how Functor or how Fmap work intuitively. So, for example, we have a box which is had the number 2 inside of it, and we do an action like we unwrap or unbox the value inside the context or inside the box. We take number 2 out of the box, right? And then we have a function plus 3, and we apply the function plus 3 to 2, right? So the result of this is 5. Now we have the 5 as a result. We do the next step is we put the value 5 into the box again, or regraph the value in the context again. So this is kind of like the visualization help you to understand the Fmap easily. So in another way, you can understand like this. So if you have a box or the structure of or the context, Functor here, the F, we at the beginning of time when I learned Haskell, I confused about F here. It's kind of like F is always denote as a function, but here is F here. F we can like denote by using K or whatever we want, but they using Haskell, they using F because like it can refer to Functor easily in this context. So F here is a kind of like a box or a context or computation which is have a value inside of it, right? And we have a function outside of the context, and we somehow need to apply this function to the value inside of the box. So we have two ways. It's kind of like visualization. This is one way. So we take the value A outside of the F, right? As this image illustrates to you. We can understand or we can see in a different view is we need to lift this function into the box somehow, right? And the Fmap is kind of like, okay, I have a function and I have a box and it has A inside. So the Fmap function is kind of like have a magic way to lift this function inside of this context Fa, context F, and then apply the function to the value A. And then in the context F, we have new value which is B. So that is another way to understand Functor, right? So here is kind of like some example of Fmap. So let's try this one. For example, I have the list from 1 to 5, and I want to multiply it by 2. So I can use like this lambda x, the arrow, and x the x multiple 2. So we will have like double value of the list of from 1 to 5. So we can write in another form is asterisk 2, right? So it's the same because here is the point free function of this one. So this is the Fmap function of the list. How about like maybe structure? For example, I have the church 10, and I have a function. I want to apply the function multiple by 10 to this structure. This is maybe data type, right? And this is just 10. So let's try. So now we have like the value of it is just 20. So we can understand that like we have a function and we try to lift this function into the context church, and it will return the church 22. And for the maybe data type, we have nothing as well. So it means that we have nothing inside the box. We can say like that. And the result of this is nothing. So that is the functor. So next one is applicative. So the main function of applicative is apply function or app. So let's say like we pronounce it like app function, and case is an applicative, or we can denote it as uh, any character. Okay, so in Haskell they normally using the case for applicative, and we have a function. Okay, now we have a structure which is contain a function arrow or to a contact which has a value and return a contact which has a new value b. So the difference between functor and applicative is you can see that like this one, the function is outside of the context. This one, the function is inside of the context here. So we sometimes or usually we saw that like in many cases that like this function already inside of the context. And if we have some case like that, applicative or apply function is the way to dealing with that. So it's kind of like the difference between like Fmap and app function in applicative is the function is inside of the context. So we no need to leave it. So let's take a look at this illustration of applicative. So we have the function already inside of the box. This function is plus 3. So inside of the box, it means like here the choice is the box or like the context or the computation. So this function already in this computation, right? Now we want to apply this one to the a box which is contain number 2. So the thing is in this picture is illustrate as we use hand to take the function outside of the box and use the hand to take the number outside of the box, and we apply the function plus 3 to 2, and we have the value, the result is 5, and we do another step which is not here, is like put the number 5 inside of the box into the box again. So this is one way to understand that. So it means that like in this case applicative here we can understand that like the function already inside of the context. So that is the difference between Fmap and app function of applicative. So let's do some example of this. So let's say here you can this one is using you use the Fmap, right? Let's try to use the applicative or apply function. So this function is not inside of the context. So now we want to put this one inside of the context. So if we want to put it inside the context, we can use something like this. It is from the list. So list of the function and list of elements from 1 to 5, which is the same context, right? And the function here is already in the context of list, so it should need to apply this function to this element. So we have the same result as we use the functor here. And next, we can try another way. Is we're going to try to peel and multiple 2. So the thing is here is spill is kind of like we try to leave some function which has no context, and we wrap that function. It's kind of like push this function into the context which is relevant to it here is the list. So let's check type of pure. Is pure function is kind of like take an a value and put this value inside of a context. So that is applicative. And the main difference between a functor and applicative is the function here is outside of a context. The function here is inside of a context. So if we don't have the function this function inside of the context, we can use a few function as here to 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 put this function into the context, and we can use this function which is called apply. So that is the applicative. The next one is monad type class, the most important and interesting type class when we learning Haskell. And every learner, when they learning Haskell, they try to understand monads as fast as possible, and then they hit the word. So that's the reason why in this video I keep the order in this, starting from the basic one, monoid, functor, applicative, and then the monads. So there's a reason why the order should be like that. So let's start. So this is the type signature of the by function, the main function or the most important function of monad. So let's denote M is monad, and we have M of A, or the structure M which contains A inside, and then we have a function which takes A outside of M in the context. Oh, we have the function A to M of B, which is A here is a value which is taken out from the context of M. Okay, and the result of this is MB. So it's very confused when you start to learn Haskell and when you read about this. Or like they have many quotation is a monad is just a monoid in the category of and a functor and what matter. It's kind of famous, and it kind of like curious the learner and make the learner confused a lot. So let's forget about the meme, and we can see the monad or the bifunction in a different point of view, and we can understand this. So this is the visualization or the illustration of monads. Okay, let's take a look at this picture, which is illustration for the bifunction of monad. So let's say that like we have a box which has a 20 number 20 inside of the box, and we do the first step is we unbox and we take the number 20 outside of the box, and we have a function or a tool or a magic thing, something like this in this picture, which is receives number 20 and return number 10, which is inside of the box. Remember that like the number 10 here should be inside of a box, right? So it's kind of like we have M of A or box of 20, and we have a step like we take out number 20 outside of the box. We take out value A outside of M, and we have a function which is receive number 20. Here is number A, value A, and return a box of 10 or M of B, and we have the final result is M of B. So this is the final result, right? And we keep doing that continuously like this. And next we want to take 10 out of the box, right? And then we have the tool which is the same as previous, like it received the value 10 and it returned the number 5 inside of the box. And then we have the step is we take out number 5 outside of the box, and we use the tools which is receive number 5 and return nothing. So if we have the computation continuously, or we have some action which is to have the same action but which is repeatedly, and in that case, in that sense, we can use the by function. So by function is used for that. So that is the visualization of it. So it's kind of like this is the type signature of it, and this is the illustration of it. You can see that, you can think about that like you have a box contains something, and you take up the value inside of the box, outside of the box, and you do some calculation or some magic thing, which is return a box contain a new value, and doing that action continuously or repeatedly. Okay, so let's try with before going deep or going further. We will try with some example. Like for example, I have just a just one, right? And then uh, take the value one outside of the box. Here is just x, and I want to x plus x multiple by 2. So let's say like number 5. So I have like x multiple by 2. So now it have the value is 10. So and I want to make it like the result is still inside the box. So it should be just 10. Or you can use like just here, right? And then you want to multiple or like plus, apply the plus function. Now we have y and y plus 9, and we use pure function here. And okay, so we substitute this one, and the final value is 19. So we can see that like this action or this computation is repeatedly, and we can use the by function. Okay. So in this kind of, this just like the explanation of what we have explained here. So I will skip it. And I have an example of like in real life, we have another reason to use the monad or use the by function. Let's say that like we have maybe plus, which is like a function trying to plus to integer, but we wrap the integer inside of the maybe type class. So the type of maybe plus here is maybe integer, a row maybe in, and a row maybe in. So this is the implementation of the maybe plus. So if we have, in this case, the way we implement this kind of like, we need to check like, we use case of to check like, is it nothing or not? If not, it has just a, and then we continue to do the case of to check like whether MB is nothing or not. So if it's just B, we return just A plus B. So we can build the helper function like this. So because we see that like we use case of, and we can try to reduce the repeated code like using the helper function. So we can write a helper function which has types like this. So maybe of A, and then function which has type maybe of A, and then we take the value A outside of maybe, and then we do something and return maybe of B, and then we have the final result is maybe of B. So this is the implementation of the and then function. So kma of, if it's return nothing, we return nothing, and if just A, we just A here, right? We have the value, we use pattern math here to get the value A inside of the box. Here is just, right? We have the value A. Now we can apply the f function here. F has type A to maybe B. So if we apply f to A, we have the return is maybe B, which is fit with this type signature, maybe B. So now this is the maybe plus prime, which is use the helper function. So it's now is very neat, just one line of code. So we can write like this, maybe plus prime, MA and MB. So MA, and then we take the A outside of M. We continue with mb, we take the number b, value b outside of the m, and we return just a plus b. So that is the way we use the helper function. And let's take a look at this one. So this is the maybe plus prime, and we already explained that, or how we trying to refactoring the maybe plus function. So if we see that, like, if we write two of this function, it's kind of, if we consider that like the written function like this is like, it just take like from 8 to 15, it's just like 8 line of code, right? And here is take more line of code, but in the code structure part of it, this one is cleaner. That's the one reason why we should use this helper function. Another reason is if we have a requirement that like, if we have another requirement like you need to write a function with either plus and you still have the same, right? Helper function with the plus and either plus with the and then helper function. So please ignore this one. If you're interested on this one, you can visit the link I attached in the video. Okay. Or and next one is list plus, so which is have the same requirement. So the context now is like list of in. So you can see that like we have some pattern or some code that repeatedly, and we need the way how to generalization this one, and that is where monad or by function sign or useful, help you to reduce malware cost. So the thing is, if we use the by function, or if we use the by function, so this is the only one solution. So let's say the m plus is the one stop solution or one stop function, which is plus kind of like maybe something or either something or list of something. It's kind of like m of something. M here is monad, right? And a is here, the constraint of it is a number. So this is the only one solution because we know that the type of the by function already. So the m plus which has two parameters. The first thing we can do is like we take m and a, m of a, and we use by function to take out the value inside the m context, right? And then we touch the m of b, mb, and we use by function to take out the b value inside the m context. Now we have a and b already. Then we apply the function plus to a and b, right? And a and b here is not in any context. So here we can use return a pure function to put this one in the monad or in the context of computation again. So that is the useful or the application of by function. So you can see that like we in this case we have like the code duplication, and with the helpful or the useful of monad or the by function, you can write it with only one line of code like this, very neat and clean. So that is the powerful of monad. So another one is the next one is the relation between function application, monoid, and app function of applicative. So let's see. So the type signature of function application is A to B in parentheses, and then to A and then return B, right? And append. So type append is F to F to F. So it's kind of like the structure is the same. And let's see the type of function of applicative. So the difference with the functor is this one already inside of the context, and a row with app function takes a function already inside the f context to fa and return fb. So you can see that here function application, if we put this one inside this one and this one into this one, this one into this one, so you can see that app function of applicative is kind of like somehow related to function application, and Monoid, which is here is in Mapan, the structure is the same. The function applied to the value inside of the context or the inside of the structure. So that is the relations between function application, Mapan, and apply function of applicative. So next one is the relation between functor Fmap of functor and by of monad. You can see, no, this is not by function, this is flip by, which is we swap the parameter of the by function. So this is type signature of Fmap, which is have a function from a to b in the parentheses to f of a and to f of b. And this is the flip by function which has a type signature. This is a flip by, right? So that we change we swap the function ahead. So a function which takes a to m of b in parentheses and to m of a and return m of b. So you can see that like if we consider f and m, which is the same, right? The structure outside of a, so you can see that it's somehow same, right? And the different thing is here is a to b and here is a to m of b. So b is inside of the context already. So this is the explanation of the relation between Fmap and flip by. Let's see. So if this one is the Fmap, right? So this is let's say that like we apply the Fmap function to m of a, and we have a function which is applied to the we have a function a to m of b prime, right? And if we're using Fmap here, we will return m of b prime. So you can understand, like you can imagine like we keep the structure here, right? And we leave this function inside of this context m. So this one is like we keep it. And a now, because of we apply the fmap function, a here is now m of b prime. So we have m of b prime here. So if we somehow have function which is convert this two-layer structure to only one m of b prime, and there is kind of like join function have the type like this. We have type of join. So we need to import area.monad so we check type join. So m is monad. So m of a, if we're using join function, it will return m of a. So there's kind of like the transformation here. So here is two layer. We can form the result, which is has one layer only, but the condition here is m and m is the same type. So m and m here is denoted as the same type. So we have a function which is transform the structure, like here is two layer of the structure m into one m of b. So if we replace this one into this one, so we have kind of like join of Fmap, right? Have the type A to MB prime and MA, and here MB here MMB prime, which is return MB prime. So we have join of Fmap which have the type A to MB prime to MA to MB prime. So let's check the type of byte, right? And let's take the type of flip byte. So you can see this is the flip byte, right? And this is the flip byte A to MB, MA, MB, and we have the type of join of Fmap, which is the same if we replace B with B prime. So A to MB prime, A to MB, MA, and MB. So it means that like flip by or this character or this kind of like equal angle or less than equal less than. Sorry, my bad English about this one, but I actually I don't know how to pronounce this, but I normally call it a flip by. So flip by is actually the combination of Fmap and join function. So with this equivalent transformation, we can conclude that by function is kind of like somehow starting from the Fmap, and if we have a way to form the structure, a structure of two a, type, a parameter which has two layers of m to one layer of m only, and we can say that the flip by is just a combination of join and Fmap. So with that way of thinking, I think monad or the bifunction of monads is not easy, no, not difficult to understand, but it's kind of like a reasonable evolution of the thinking process. So thank you for watching this. See ya.